In this lecture, we're going to introduce the concept of measures of association, and we're going to examine that through the statistical procedures called correlation and regression. And the statistical procedure is applied to studies that are correlational in nature. And studies that are correlational in nature are intended to examine relationships between different experimental or different research variables. And a couple of key points before moving on to begin with is that with a correlational study, we typically rename the dependent variable, which is usually our outcome variable, as the criterion variable. This is the variable eventually in this type of statistical approach and research study that we're trying to predict. The independent variable, very commonly used in describing many research studies, typically this is the one that you would see depicted on the x-axis. If that graph is not a frequency distribution, the independent variable we will call the predictor variable in these types of research designs. And so when we want to examine a relationship between two variables, really the first step is to make a scatter plot of the data, and we'll see that here in this lecture. And the researcher should always perform what I term as the intraocular test, where the researcher just basically looks at the graph and gets a subjective impression of what the data on the graph are depicting. The next question the researcher should ask is, does this graph make sense based upon the researcher's understanding of that research question? And so can the researcher explain the outcome of that graph in psychological terms, physiological, sociological terms, whatever is driving the research question? And in this example, this is just a hypothetical example where a relationship between two variables, number of children, and in this hypothetical study, it's the hours per week husbands spend on housework. And in this particular study, there are a number of cases identified by individual families. And you can see that the number of children across the cases in this study varies from as low as one child to as much as 5 children. And the number of hours spent on housework varies as well. But when one looks just at these two columns of data, it's hard to examine if any relationship exists. And so what we do in a correlational study to see if there is a relationship between these two variables, we make a scatter plot, and that's what we see here on the right-hand side. So in the scatter plot, we place the variable number of children on the x-axis, and recall from the previous slide, the variable that we plot on the x-axis is our predictor variable, and based upon, in this example, the number of children, can this predict the number of hours spent per week conducting housework? And so the y-axis variable, our main outcome variable, is what we call the criterion variable. Typically, we would call this the dependent variable and this the independent variable. But if our intention is to carry out a correlational analysis, then we use the terms predictor and criterion. And so what we see here on the scatter plot are a number of blue dots, and each blue dot represents a single case that we have on our table. Before we get to that, the line here is what's called the line of best fit, or the regression line, and that will be addressed a little bit later in this unit. But the line of best fit or regression line, those terms used interchangeably, is a line that best describes the pattern in the data. And so the line here illustrates that there is an upward trend or an upward pattern as the number of children in these families increases, the number of hours per week spent on housework also increases, but not in a perfect manner. And so if we take a look at the first family here, the first case, this first family had one child, and the number of hours spent on housework was 1 hour. And we see here, this is just one case. The next case here, we see that this family has two children, but only 1 hour spent on housework. And so what we can say here, just by looking at these two data points, that the number of children does not predict how many hours are spent, because both are 1 hour despite having a different number of children. But when we put all of the data on the graph, what we see is that we have this upward pattern. So the blue dot represents the actual value, which is different than the line which describes the general pattern. And so the equivalent spot for the x-axis on the line is called the predicted value. So if we were to try to predict for this family, we would get a value just above 2 hours per week. And so this difference is determined to be measurement error, or the measurement variability on the scatter plot. So overall, the correlational analysis is intended to describe the direction and the strength of the relationship between two variables. And so what this does is this indicates the consistency between the two variables in the data and examines the variability in the scores along the y-axis as a function of the scores along the x-axis. And so that is what is used in a correlational analysis. The next step is what's called a regression analysis. And so the regression analysis, as we saw on slide number 3, a regression analysis will involve development of the regression line, or the line of best fit, that best describes the pattern if the pattern exists in the data. And in doing so, the regression analysis will provide a degree of accuracy of a prediction. So a prediction could be very, very accurate or not accurate at all. The regression analysis will establish that. And so to examine different patterns in the data, we begin by looking at what's called a positive relationship. And so if we take a look at these two different graphs, what we're trying to do here is to predict a criterion variable, or the y variable. And for our example, we're going to say the y variable is the grade point average, an overall average among for students. The x-axis is a measure of the lectures attended. And so along the x-axis, as we move from the left to the right, that would indicate a greater percentage of the lectures attended. And if we just take a look at these two graphs, we can see a general upward pattern that is quite perfect with the graph on the left, and not nearly as perfect with the graph on the right. What's important to note here is that correlation and regression analysis, this is the key aspect to it, it does not establish cause and effect. So although we have these very good relationships, and we'll fill in this graph here in a moment, we cannot say that increasing lecture attendance will cause an increase in grade point average. We can only say that there is either a strong relationship, a moderate relationship, a weak relationship, or no relationship at all between those two variables. So the grade point average would be plotted along the y-axis as a percent, and the lectures attended as a percent of total would be plotted along the x-axis. Now, the graph on the left would be a depiction of one of the studies. If we carried out the same study in a different group of people, we might get the graph here on the right. But the graph on the left illustrates a perfect relationship. So if we were to draw a line of best fit, we see that the line cuts through all of the data points. No single data point lies outside of that line. And at the bottom of the graph here, you see that we have what's called an R value of 1.00. The R value is the statistic for measuring the relationship in a correlational analysis. That's what we're looking for. And the maximum value of a statistic for correlation is 1.0. We can't have a value greater than 1.0. So an R value of 1.0 would indicate a perfect correlation between the two variables. Now, a more realistic depiction of this is what we have on the right. So what we have here on the right is we have a greater degree of scatter, and if we were to draw a line of best fit, the line would certainly not cut through all of the data precisely. So there is variability about the line, but the R value of 0.94 would still indicate that this is a strong relationship, despite the fact that we have some scatter. The next type of correlation we can have is what's called a negative relationship or an inverse relationship. And the inverse relationship tells us that as the value on the x-axis increases, the value on the y-axis decreases. So as one goes up, the other goes down. And so the next example here is if we examine people who spend more time in the gym, which would be our x variable, are likely to have less body mass. And so the key outcome variable here is body mass. And by looking at these two graphs, what we see is that there's a general pattern as the variable increases in value along the from left to right along the x-axis. There's a fairly clear pattern that the value of the y variable also decreases. However, it's important to note here in a study like this finding would not mean that spending more time in the gym will decrease a person's body mass. These data were collected from each person only once in order to try to establish a cause and effect relationship between these two variables. A different experimental design would have to be incorporated. So what we see here is body mass is our key criterion variable, and gym time is our predictor variable. And as we saw on slide number 5, these two graphs illustrate two different studies carried out likely in two different locations. So the negative relationship is still quantified by an R value, but the R value will be a negative value, and the magnitude of it will indicate the strength of that. So here we see quite a bit more scatter than we do on the right-hand side, and that scatter will tell us that the relationship may be strong, moderate, weak, or no relationship. In this particular case, the amount of scatter still illustrates a very clear pattern as we move in terms to the right. So as a person spends more hours per week in the gym, they are likely to have a lower body mass, but that is not cause and effect. On the right-hand side, as we saw on slide number 5, we see a perfect relationship that if we were to draw a line of best fit, that line would cut through all of the actual data points here. And so a perfect relationship, which is not something that we see in research, but it illustrates this point. The maximum R value, similar on slide 5, would be 1.0, but because the relationship is inverse, it would be a negative 1.0. So once again, the largest magnitude if we just take a look at the absolute value, would be 1.0. Anything less than that would indicate that the data points are starting to scatter. If we take two other scenarios here, we take a look at this scenario here on the left. Here we see a scatter plot with quite a bit of scatter, but if we take a close look at it, we can see a general pattern. As the x variable increases to the right, the y variable also will increase. But note that the r value is quite a bit lower than the ones we saw on the previous slide. So as one variable value goes up, the other variable value goes up, and that's a positive correlation. But there's quite a bit more scatter about that line. So it's far from a perfect relationship, but this would probably be best described as a moderate relationship between the two variables, and that's confirmed by this R value of 0.44. So the key points here on the left is that this is a positive relationship, but could be considered weak depending upon the research question. It could also be considered moderate depending upon the research question. And so whether we consider it weak or moderate is the reason for that is because of the scatter away from the line of best fit. And so because we have so much scatter that we can't state that this is a strong relationship. And one example is if we pick one point on the x-axis and draw a vertical line, we see at a single point on the x-axis we have multiple y values. And so that would clearly indicate that we don't have a strong relationship between these two variables. Now, if we take a look at this graph on the right, clearly just making a visual observation here, we clearly see that there is no emergent pattern here. And so because there's no emergent pattern, we would just conclude that there's essentially no relationship. And we can quantify that there's no relationship with an R value of 0.0. And so the lowest possible value a correlational analysis could deliver in terms of its magnitude, its absolute value, is 0.0. The same rule applies if we have a negative relationship. So with a negative relationship, a negative 1.0 indicates a perfect correlation. That is inverse. We take a look at another example here. These are actual data obtained from the 2009 track and field or athletics championships for the 100-meter dash. And in this study, we generated a scatter plot where we looked at reaction time coming out of the starting blocks for these 100-meter sprinters, and this was in the final heat. And what we have plotted along the y-axis is the key outcome variable for this event, and that's 100-meter time. So a lower value would indicate a better performance if a person can cover 100 meters in a shorter period of time. And the question we're going to ask here is, does a sprinter's reaction time to the starting gun, is that important in this race, and can it predict how well a person can perform this race, with the idea that reacting to the gun faster would allow the sprinter to get into their running stride earlier and get to the finish line faster. So if we take a look at some of the descriptive statistics from this event, we see that the average reaction time for the 8 sprinters in the final heat was 0.139 seconds, so much less than a second, with a standard deviation of 0.015 seconds, and had a coefficient of variation of 11.01%. In terms of 100-meter time, we see that the average time to complete the race was 9.92 seconds, at a standard deviation of 0.3, but the 100-meter time variation was much tighter than that for the reaction time if we take a look at the coefficient of variation. So the coefficient of variation was much tighter for the key outcome variable or the criterion variable than it was for the predictor variable. And so we have our predictor variable along the x-axis, and how quickly a sprinter reacts to the starting gun, does it predict how well they'll do in the race. Now, if we take a look at the scatter plot, if we take a look at all of the data, there appears to be no emergent pattern. However, if we zero in on this cluster of data, so if we just ignore these two for a moment, now we start to see a clear pattern here. And if we estimate a line of best fit to describe the pattern, this line would be described as inverse. So as reaction time increases, 100-meter time will decrease. And what that suggests here is that the slower the sprinter is in reacting to the starter's pistol, they'll actually run faster and have a faster 100-meter time. So we would make this conclusion based solely on these data. We have the question marks here generally because in training for a 100-meter dash, typically athletes and coaches want to be able to react faster coming out of the starting blocks. But in this very small study here, very small sample size of the 8 fastest sprinters in the world in 2009, we see in this cluster that principle was not applicable and was actually the opposite. Now, if we turn our attention to these two data points here, these two data points seem to stick out from this main cluster. And this particular data point is called an outlier. So the outlier is a data point that tends to have a large vertical deviation from the rest of the data. So this one tends to stick out quite a bit, and there are mathematical ways to establish an outlier, but we're just making that determination visually here. This other data point is actually called a leverage point. And the leverage point is one that has a large horizontal deviation from the rest of the data. So if we take a look at the outlier's vertical deviation, take that over to the y-axis, we see that it's quite high on the y-axis, but this leverage point here, if we follow this one to the y-axis, we see that it falls within this cluster that we have boxed right here. So we would not describe this as an outlier. Conversely, if we take a look at the leverage point, follow it down to the x-axis, we see that this particular person has a large leverage point because it's sitting far to the right of the rest of the data. And the outlier here, if we follow it down to the x-axis, would actually fall within the cluster. So it's important to note that when we have a scatter plot, visually identifying data that seem to separate quite a bit from the central cluster, we have to determine if it's a large vertical deviation or a large horizontal deviation. And one last point is that some data can be both an outlier and a leverage point. So this ends our first video here on correlation and regression analysis.